Okay, more problems from section 9.5. Let's take a look at number 9. And again, we just want to determine the convergence or divergence of these series. And number 9 is the natural log of n over n. And n goes from 2 to infinity. So since for n greater than 2, the natural log of n over n is greater than 1 over n, because the natural log is greater than 1 of 2 or 3 or 4, not 1, but for 2 or 3 or 4. So as we go out to infinity, that's going to end up dominating whatever happens from 0 or 1. So this is always greater than that. Then we can use the direct comparison test. And this diverges, because that's the harmonic series. That's the P-series test. That's the harmonic series. So since every term here is greater than every term here, and this diverges, that diverges by the direct comparison test. So there you go. Okay. On number 10, I think I used the integral test on this one. The summation from n equals 1 to infinity of 1 over 2n plus 1. This looks like a situation that would apply, or that we can apply the integral test to this. So the f of x equals 1 over 2x plus 1. For x greater than 1, that's that same 1. And that is continuous, positive, and decreasing. So we know that this series will behave like this in proper integral. Then again, we said it b goes to infinity, a 1 to b of 1 over 2x plus 1 dx. And then I'll need a 2 here because I'm going to try to make this 1 over u du, take the natural log. So, but the du has to be 2 dx, the derivative, that's 2 dx. So I'm kind of doing u substitution in my head. So I need a 2 here, so I have to multiply by 1/2 to get that to balance. And now I've got this in the form of 1 over u du. There's my du. So that's going to be the limit as b approaches infinity, and I can take that 1/2 in front of the natural log of 2x plus 1, okay, from 1 to b. So if we take the antiderivative of this, I should say I keep this 2.5 in front. If I take the antiderivative of this is 1 over u du. That's going to be the natural log of the absolute value of 2x plus 1. But since x is going to be going from 1 to infinity like n, I don't want to need the absolute value bars, so it's going to be positive. And then I've got 1/2, and then I can evaluate this. Natural log of 2 times b plus 1 minus the natural log of, this is b, not 26, this is b, 2 times b plus 1. And then I put 1 in here, so I've got 2 times 1 is 2, plus 1 is 3, and then the natural log of 3. But that doesn't really matter what this is, because this 2b, b is going to get really, really big, and I'm multiplied by 2 also. So it's even going to get bigger. Add 1, this is going to be infinity over here, which makes everything infinity. So, therefore, it diverges, so it equals infinity. So since my integral diverges, it doesn't come to a value, and so does my series, so my series diverges by the integral test. Okay. And then number 11. If we look at number 11, I can rewrite this 1 over the natural log of 2 to the n as 1 over the natural log of 2 to the n, and now it looks like a geometric series with a common ratio of 1 over the natural log of 2. That's my ratio. When I have this, when n equals 2, I just multiply by that, so that's my common ratio. And if I put that in my calculator, that ends up being approximately 1.44, which is greater than 1. Therefore, the series diverges. That's real nice about that. Okay, that's real nice. That's no problem. That should be very easy because of our geometric series. That's why we spent the whole first chapter on geometric series. They come in real handy. Okay, and just one more here, number 12. Kind of finish up this part of this assignment. And number 12, I have the summation 1 to infinity of 1 over the natural log of 3 to the n. Well, again, we can write this as a geometric series. I could just put 1 to the n is the same thing as 1, so I could make this as 1 to the n over the natural log of 3 to the n, or just 1 over natural log of 3 to the n. That, again, is a geometric series, and what's my ratio? My ratio is 1 over the natural log of 3. Okay, 1 over the natural log of 3, and if I calculate that, that's approximately 0.91, which is less than 1, so therefore it converges. Okay? And I think that takes care of that.